All right. Very good to see all of you today. We're dragging behind a little bit with regard to the syllabus, but that's fine. I think we have some space because there's I think an entire week devoted to moons of the solar system at some point, and I found last year that the moons are actually very, very similar to one another, and it's not a great time to sit here for 3 hours talking about each one of them necessarily. So if we get behind, it's going to be all right. Just keep cruising along with the textbook in the meantime. All right, so last time we talked about time, right? And does anybody remember give me some feedback about time. What did you learn? Somebody, what is time? At least in the context of physics, what is time? Somebody? Don't be afraid. Say again? Never-ending thing. All right. What else? So, yeah.
I mean, it's very much a human invention to maintain order in some sense.
Yeah, it is an invention. Yeah, it's an invention, and you said it helps us maintain order. I'd say it helps us track change, right? It's sort of a measuring rod in some sense, right? So fundamentally, when we see time in an equation in physics, it means what a clock does, and so clocks are these things that we're able to measure the rate of change, right? How things change in the material world. Okay, cool. So we always need that standard, and change is going to happen with or without humans, but time, of course, doesn't really make sense without a human to remember when the clock started. So we talked a little bit about seasons. Does anybody remember why seasons happen? Yep. Tilted axis of the Earth, right? So in January, we are actually closest to the sun, all right? Which is perplexing. Technically, we're leaned more in towards the sun, so there's an argument to be made that we're receiving more sun, but that's not because the Earth itself is closest. Now, people down under have a very different perspective. And then we cracked open the topic of climate, which I'm going to continue today. And, climate's not an easy story to tell. It's a very politically fraught topic right now, which makes it really fun, because we get to explore some different controversy. And I want to try to get at the heart of why there even is a controversy, because you would think, well, taking care of the planet is a good idea. Why in the world would anybody think that isn't a good idea? And I don't think anybody does. I think it's a bit more complex than that. And so we'll carry on with that today. But after we get through climate, I want to talk about calendars and how people set up calendars. Then we're going to talk about our moon a little bit and how the different proposals for how our moon was formed. And then if there's time, we'll talk about eclipses. I do want to mention we have a nice eclipse coming up this Saturday. It's going to be I think it's going to max out at around 9:30 in the morning on Saturday. So drag yourself out of bed and go outside and check it out, because chance won't come again for a while. There's going to be another one next, April. I think it's on the 8th, but I don't believe that it's passing directly over Oregon. So I'm going to be down in Austin, where I'm holding a conference down there for my podcast, and we're going to check it out. It should be really cool. Texas, yeah.
You'll be out of the clouds there, won't you?
Yes. Yeah, it should be really nice in Austin. Hopefully the clouds don't mess up our eclipse this Saturday. They probably will. They probably will. But Texas should be a lot better. The whole, I appreciate those of you who came and hung out for the coffee hour this morning, or half hour, or whatever it is, and talked a little bit about with the small crew that the whole point of even having this class where the whole point really of you even coming to college, as far as I'm concerned, is not just to give you a credential so that you can go on and get a job, although that's obviously useful to you, But we really, really want to learn how to think about these problems, right? We don't want to just learn these facts and move on. It's important to understand why these facts have become accepted as they are. And in some sense, there's always two sides to that, right? When you examine any particular piece of information that we come across, and we're going to be talking about climate here in a second, you have to ask yourself, why did people think that this is the case? So what are the underlying assumptions? But you also have to ask, what are the motivations that drive them to maintain these beliefs, right? And then you have to also ask yourself, what are the second, third, and fourth order effects of these decisions, of these theories that we have, right? Because a lot of times, and I think this goes back to a really old idea that nothing exists in a vacuum, right? So every decision that you make, and you'll realize this the older that you get, there's nothing that you're going to do in your life that's just going to affect you. Absolutely everything that you do, even the thoughts that you have in your head, are going to boil out and find their way into the universe. And so particularly when we come up with these scientific theories and so forth, we have to imagine how they impact all of the other scientific theories and how they impact our understanding of our place in the world. And so I really want to keep coming back to these 3 points, right? Motivations, this downrange effects of these understandings, and then keep an eye on how they might change in the future, right, as we could learn more and more about those situations. So, obviously right now let's talk about climate a little bit. So climate is this long-range pattern of changes in really the temperature of the Earth over time. So I'm going to assume you guys know very little about the history of the Earth, which is totally fine. But essentially what's been happening for several million years now, certainly we can measure this for the last million years, is that the Earth periodically gets very cold and then it warms up again. There's this very regular 100,000-year cycle where the polar ice cap advances, right? At some point about 20,000 years ago or so, the polar ice caps came all the way down into Minnesota and New York City. And they obviously have retreated. Now, it's interesting because the last retreat of the glaciers coincided with the birth of civilization on this planet, as far as we can tell. There was, a lot of changes happened as a result of that, climatic changes, right? There was places that were not covered in water that all of a sudden were. And so people had to move a lot. There was a great deal of what would you say, migration as a result of that. So there's whole villages that are that they're starting to discover in the channels between England and the mainland Europe, right, that were totally dry as recently as 15,000 years ago. And all those people had to move. And so the standing theory is that they started to aggregate together and learn how to these traffic patterns resulted in the accumulation, nucleation of cities and so forth. Now what's really interesting is that people today are really, it's a very, very pressing issue that the climate is changing right now, and it certainly is. It's also worth noting that it always has changed, and that climate change has actually brought an end to every single civilization that's ever existed on the planet. And that's something that people might not be aware of. Climate change ended the Mayan civilization. Climate change ended the Sumerian civilization, right? Things got drier, the sea levels rose. In some sense, this has been a persistent problem for all of humans since ever. And the question now becomes, what do we do about it, right? And the very popular idea right now is that what we should do about it is stop it from happening. And that's an interesting proposal, that you're going to stop this, that you're going to be able to stop this 100,000-year cycle of glaciation and deglaciation. In some sense, I think that a smarter program would be how to roll with the punches in some sense, right? Now, there's people that advocate that by changing our greenhouse gases, we'll be able to actually slow down this progression. But I'm not sure that that's the best way to go. And I'm also not sure that I'm not sure that some of these narratives have the best interest of humans in mind, which is a little concerning too. So actually, in the 1970s, people were really, really worried about global cooling, right? That was what the scientists thought was going to happen as a result of these greenhouse gas emissions, because they would block out, essentially they would nucleate clouds, which would block out the sun, and it would get very cold, and we would kind of be screwed as a result of that. Only recently was it kind of realized that the temperature was rising in some sense, on the order of a half degree or something, and that we should be concerned that the ice caps were going to melt, and this would inundate our coastal cities, and this would be a problem. But there's always been a contingency of people that are very afraid, in some sense, that the Earth is coming to get us, and that, and what's really kind of creepy to me is that oftentimes those same people think that the solution in some sense is that there should be less of us on this planet. And I'm very, very skeptical of that narrative. You know, there was a big book that came out in the 1970s from MIT Press by, I can't remember the guy's name, Ehrlich, I believe, called The Population Bomb. And the prediction was kind of Malthusian in that, you know, if things continue as they are, there's going to be widespread starvation in the early 2000s, and basically everything is going to go downhill. But it didn't work out that way, because humans are actually really ingenious, and we always find ways to upscale our production and meet our needs. And in fact, there's been less and less starvation every year ever since then. But the seed of a lot of the environmentalist movements at the time gripped onto some of these basic ideas from Paul Ehrlich and so forth. And actually, there was this other book that came out here that I think is worth paying attention to. This was in 1989 by this guy, Bill McKibben. And he's kind of the father of a lot of the modern global warming ideas. And, you know, I definitely count myself among the people that really want to see humans living in harmony with their environment. But I in no way think that means that we should, get rid of ourselves in the process of doing that. And the sad thing is that a lot of the green energy movements over the last 20 years have been very expensive on the people who are the poorest, right? So in some sense, taking the coal out of people's furnaces in the third world because they need to abide by our climate agreements with regard to fossil fuel burning, it seems like a good idea, because obviously choking yourselves out with burning things is a terrible idea. But so is starving because you can't, or freezing to death because you can't actually keep your house warm, or you can't, get access to petroleum-based fertilizers. All of our food in the stores is grown, with the exception of the few of us who can afford organic food. It's all grown with petroleum-based fertilizers. Natural gas, ammonia, is the primary constituent that's used to make fertilizer, and that's the reason that we can even sustain 8 billion people on this planet right now. This is what I mean by second and third order effects. You have to really consider these things, right? It's not so simple as just, hey, let's stop taking this oil out of the ground, because you're going to hurt a lot of people by doing that at the same time, and you don't have the infrastructure ready to replace that. It can become very dangerous. And so this guy wrote this is a review from a review in the LA Times of this book by David M. Graeber, who's a chief research biologist for the National Park Service. He wrote this about this book. And I would say this book is a sort of a landmark book to describe the climate change movement at the time. He wrote of the author, Bill McKibben, is a biocentrist, and so am I. We are not interested in the utility of a particular species or free-flowing river or ecosystem to mankind. They have intrinsic value, more value than me and another human being, or a billion of them. Human happiness and certainly human fecundity are not as important as a wild and healthy planet. I know social scientists who remind me that people are part of nature, but that isn't true. Somewhere along the line, at about 1 billion years ago, maybe half that, we quit the contract and became a cancer. We have become a plague upon ourselves and upon the earth. It is cosmically unlikely that the developed world will choose to end its orgy of fossil fuel consumption, and the third world, its suicidal consumption of landscape. Until such a time as Homo sapiens should decide to rejoin nature, some of us can only hope for the right virus to come along. Yikes. All right? So this is a very, I mean, this is a perspective, like, this is a perspective I want to share with you because you're not likely to come across it in the global media right now. But I think that it's a very dangerous undercurrent below a lot of these things. And I think that it's very right for humans to be concerned with ourselves living well and in harmony with nature, right? Not as separate from nature or as some sort of scab on the earth, right? I think this is a very dangerous mindset, and I think that ultimately it can lead to horrible things, not the least of which could include genocide by starvation of billions of people. So I think we have to, again, really think about the second and third order consequences of the critiques that we make. All right, so enough doom and gloom. Just something to keep in mind as we talk about this stuff. All right, so what do we know about climate? So we, like I said, there's this regular cycle of cold and warm. How do we know this? Fortunately, we can go up to the ice caps and we can drill these cores of them. And here's a picture of one of those cores. And it's not very easy to see. I guess you can see it a little bit. There's these patterns of light and darkness, right, on these cores. You can actually see the different climate eras. And when you analyze those for different chemicals, you can actually put together a picture of how these isotopes change over time. Now, from that, we can pull out how the temperature changed as well. It's a second order calculation, so you have to take it with a grain of salt. But the basic idea is that you get these little bubbles inside of the ice core, right? And you can actually measure the amount of different carbon greenhouse gases in those bubbles. You can also measure different oxygen isotope ratios. And without boring you to tears about how the temperature is deconvoluted from those oxygen isotopes, the essential idea is that there's heavier oxygen, there's lighter oxygen. And when it's warm, the evaporation increases. And actually, the lighter elements are going to evaporate first. That makes sense, right? And so you can actually get a banding pattern where you can sort of correlate the temperature with respect to the amount of evaporation and precipitation that should be necessary in order to produce that at the polar ice caps. That's how we get temperature, right? So it's a second order estimation of temperature from these oxygen isotope inclusions. But let's take it on its face value. So let's look at, what are we looking at here? We have methane, we have carbon dioxide, and then we have temperature over here. So, one thing that's really interesting is certainly we can see that the carbon dioxide that we're measuring today, now the trace in blue that's at the top, which is our carbon dioxide levels, they're completely off the chart, as you can see. But these measurements that are taken today are not measured from bubbles and inclusions, right? They're measured from the actual atmosphere, I think, at the observatory in Hawaii. And so they're being compared to data that's from these bubbles. So you need to take that with a grain of salt as well. But these axes are also a little bit confusing, right? So the axis over here for carbon dioxide goes from about 200 to 400. The temperature scale is going from about minus 8 to 2 degrees Celsius. And so what you can see, regardless of how you interpret this, is that there's a cycling period going on. And it seems like our carbon dioxide levels are quite high compared to in the past. Here's a chart from your textbook. This is carbon dioxide concentrations for the last few thousand years. Now, it's certainly true that our combustion engines are increasing the carbon dioxide in the world. And it's certainly true that those same combustion engines do a lot of other dirty stuff as well. But it's not exactly clear how we go about replacing them in a way that's sustainable because, electric cars also require terrible, they sort of put the problem on other people. So those batteries in your phone and those batteries in these cars, they come from these cobalt mines that are mined by like child slaves in the Congo, for instance, right? It's a very dirty process, and it's not totally clear how we're going to go about doing this in a way that's, sustainable, except for, putting the burden on somebody else. So this is, again, second, third order effects. How do you deal with this? One solution might be nuclear power, which is actually a pretty amazing fuel source. It generates very little waste, as a matter of fact. And the question is that waste lives for a very long time. Right now, they bury it deep underground in a mountain. And, a lot of people are afraid of nuclear because of the bombs and so forth. But on its balance, it's far safer. If you look at the amount of people who have died in nuclear energy accidents, it's nothing compared to the amount of people that have died from combustion, coal burning, all of the downstream effects of that. I mean, it can get really, really gross. I grew up in Ohio, and we have all these coal burning factories out there. And when you fly in, you can see them, and it's this big, gross yellow layer of junk that hangs over the atmosphere in the countryside there. And people are breathing that, and people are dying, and it's quite terrible. So I don't know. It seems like nuclear is probably our best option, in my own estimate, for how we actually get around this. Cleaner batteries, better battery technology, finding ways to really take care of the people that are doing that mining, despite the fact that they're not in our country, would be really something to consider. All of these second, third order effects, you can't think about just getting rid of burning things without thinking about exactly how you're going to deal with that going forward. Also, this is kind of interesting. So if you look over millions of years at sedimentation and core ice cores, you can see that actually the variation's been quite extreme in the last few 100,000 years, or say a couple million years compared to the deep past. And it's unclear to me whether that's just a measurement artifact, right? If this stuff's really old and disintegrated and it's just not reliable, or if things are really quite messy right now, right? There's huge swings. But as you can see, these huge swings seem to have been happening for the last 500,000 years, which almost certainly has nothing to do with us. So what's going on? What's even causing these swings, too, is a really interesting question. So why do we have glacial periods? Why do we have interglacial periods, right? This is actually a very tricky question to ask. Now, this is just the last couple 100,000 years of glacial and interglacial cycles. And it's kind of interesting. If you look at this, it was actually much warmer in the last interglacial cycle than it is today, by a long shot. It's also unclear right now. We're on this plateau over here to the right-hand side. It's unclear what is actually going on with our temperature right now, right? I mean, is it going to go up or is it going to go down? Sometimes it seems like if you go back 400,000 years, the temperature climbs for a good several thousand years before it drops off abruptly. And so there's a lot of open questions here about what's going to happen. And it's tangled up with a lot of motivations about what should be done about it. And there's not an easy answer to give to that. But I would say that you need to think twice before you advocate any particular solution, because there's a lot of people outside of your immediate surroundings that would be affected by that. People who might not have the same voice as someone in America. So what's causing these? That's the real million-dollar question. And I would say that it's somewhat an open question still, to some extent. So the most popular explanation was provided, this is probably in your textbook, by this Serbian geophysicist named Milankovic. And Milankovic analyzed a number of different cosmic cycles that are going on. You know, how the Earth's tilt changes with time, how the precession, that is how the actual axis turns over time, over thousands of years, how there are feedback loops that build up. There's this concept called albedo, which really has to do with the reflectivity of the ground and how that changes with cloud cover and so forth, and how all of these processes can lead to this kind of bistable system where things switch. Of course, as the ice poles melt, they also release a lot of carbon, right, from dead matter that's in there. Let's say the plants take over, right? They love breathing this carbon. So at some point, the plants, I think I mentioned this last time, but in recorded history, it's never been greener on the planet. Actually, in the last 15 years, something like there's been a 15% increase in greenage of the Earth, right? So something like an area the size of the continental United States has been added as green space to the planet in the last 15 years, right? So at some point, there's this feedback loop where the plants start eating all of that carbon, right? And that seems to certainly be happening. And it's really quite fascinating how that process happens, because the plants breathe, just like we breathe oxygen, the plants breathe carbon dioxide, actually. And so where is all this greening happening? It's actually happening in the drier regions, the more arid places that weren't typically able to sustain plants in the past, because those plants breathe through these tiny little mouths all over their leaves, these little pores. And what happens is they have to open these pores up in order to breathe, and they lose water when they do that. And so it's very difficult to grow plants in dry regions as a result of this. But if there's more carbon, actually those plants don't have to open their mouths as big. And so they don't lose water as fast, and they can sustain themselves in drier climates. And so there's a feedback loop in all of these things. There's a natural cycle to that. I think that actually, there's some people who advocate that actually planting, right? Planting ferns. There's a fern called the Azolla fern, which has a really interesting historical precedent, but it's a great carbon sink. It can grab up lots of carbon, right? And so, perhaps like the solution set in some sense lies less in taking away the energy sources of poor people and more in actually planting and greening the world so that we can deal with that carbon to some extent. There's this event that actually happened where, I don't remember when this was, but a long time ago there was a dip in the carbon levels, and what had happened was that there was this fern growing in the polar regions, and as the ferns died, they sunk to the bottom of the ocean with all of the carbon that they'd sequestered, essentially, in their bodies, right? And this led to a great dip in the carbon levels. And so there's a huge movement of people who are trying to plant Azolla ferns all over their water supplies, right? If it can grow like on a marshy climate, which would slow down evaporation, it can also lead to, and it has a great carbon sink at the same time. So planting is a really interesting solution. So anyways, Milankovitch had determined that all of these different cycles could sum up to give us this temperature swing. So we have the axial tilt, which changes over time on a different time scale than the actual temperature. The eccentricity of the Earth, so how elliptical our orbit, it changes over time. I'm not sure what this one is. I guess this is like when we are actually closest to the sun changes with time. And then the amount of sun that we receive over time changes as well, because the sun itself has cycles, right? The sun, I don't know if you guys are aware of this, and we'll talk about it more next semester, but the sun itself is a very dynamic entity. It puts out more UV sometimes than others, and it has this 10, 20-year cycle that it goes through, these solar cycles. And then there's major and minor cycles too that are conglomerates of all these other cycles, right? We're actually entering into a small minimum right now in terms of the sun's solar output. And so that should be interesting. I would not be surprised if that leads to some cooling on its own. So all of these cycles, Milankovitch integrated them all together and proposed that they could explain the Vostok ice core that we've been talking about, this cycle, the glacial cycles. It's not perfect, right? There's some agreement with regard to Milankovitch's model, but it seems to be off by a few thousand years. There could be hysteresis, like we talked about, where things take a little while and they lag behind. That's possible. It's a very interesting proposal. There's also, if you look at, so this is the way that our poles change every year right now. So this is looking at the North Pole, and it's a very predictable, interesting pattern where, as you would expect, the polar ice and snow reaches down kind of uniformly from the North Pole every year. But there's something very different that happens, or at least happened in the last glaciation. So if you go up to Canada or Minnesota, even New York, you can actually see where these glaciers came down. There's these, they leave behind all of these pebbles and boulders and so forth. It's quite something to behold. You can also see the indentation of the land where the glaciers had basically plowed their way in. And one thing that's very, very interesting and something to consider is that during the glaciation, the ice sheet cover was not actually centered over the North Pole. It was centered over Greenland, which is very, very perplexing to me. because unlike the seasonal variation, we actually have a situation where the ice cover is shifted slightly downward. And so I'm not sure that Milankovitch addresses this problem itself. But my point is that there's some really interesting open questions about why these glaciers happen and why it is that the currents would change in the world in such a way that Siberia was essentially temperate during the last glaciation period, right? They find these mammoths and stuff in Siberia that died during the last glacial period, and they have these summertime like buttercups and very temperate flowers and grass and plants in their bellies, right? So that's very strange. It's not a simple seasonal variation that we would expect if we were thinking that the overall pattern of the weather on Earth was changing uniformly. There's something more to it. And here again is a little view of the indentation of that glacier. And you can see that it's centered over Greenland, not the North Pole. Very, very interesting. Okay. Does anybody have any questions about climate? Yes?
Does all that ice forming, coming down, does that affect our wobble on our orbit with all that weight?
Well, this is an interesting point. So there was a gentleman named Hapgood who wrote a book about this. I think he called it The Earth's Wandering Pole. And I think today most people consider this idea to be sort of pseudoscience, that the pole would actually pull the axis of the Earth off a little bit. But actually, Einstein wrote the foreword to Hapgood's book, and it was entertained very seriously in his day. And so it's an interesting proposal. The discrediting of the idea relied upon the idea that there wasn't enough viscosity. So Hapgood's basic thesis was, just to clarify, that there's a somewhat viscous layer underneath the crust, which I think most geologists would agree with. It's the basis of plate tectonics, which we'll talk about later. That this viscous layer would, if the mass of the crust was offset slightly, that it would actually lead to the whole crust slipping, essentially, all at once. And so the glaciation would happen very quickly, which is... And actually looking at the way that this was debunked is very political in the sense because, look, in the 1800s, there was essentially two camps. There was one camp of scientists who essentially were biblical fundamentalists, and they were advocating something like the Earth is about 6,000 years old. And there was the other side that was like, absolutely not. Now, the biblical camp were deep catastrophists. They believed these flood narratives were to be taken literally. There was periodic catastrophes, God would smite people. And so the other camp, which ended up prevailing in the 20th century, was very anti-catastrophism. And actually today, like most scientific theories lean heavily towards anti-catastrophism. That's why you're not going to see a lot of literature about the instability of the solar system or things like that, right? It's deeply unpopular to be catastrophic in your imagining of things. And so, Hapgood's idea fell out of favor. But I think it's an interesting proposal in any ways. And it really comes down to a quantitative mathematical argument about the viscosity of the crust and whether it's capable of actually boosting that kind of a slip. So, yeah, I don't know. I'm still on the fence. It's a wonderful book, though, to read. It's just very, very intelligent. And like I said, Einstein wrote a very nice foreword for it. And I recommend you read it, if for no other reason than it's just sort of fascinating. And people used to be able to really write well back in the early 20th century and before. They're just such good writers. It's kind of incredible. There's such captivating prose, really, in a way that most scientific writing today just kind of makes you want to fall asleep. Any other questions before I move on past climate? CO2, carbon, global warming. All right, we can talk about it later if you have questions. You don't want to chime up right now. I mean, there's one thing I guess I just want to close on, which is that, look, carbon, something to be concerned with, perhaps. Let's think about it. Let's think about what we can do. And there's, like, I put a few proposals on the table today. The greening of the world is essentially a wonderful solution as far as I'm concerned. But I am concerned, and I mentioned this last time, that if we get too obsessed with this one molecule, we might miss other things that are actually more dangerous. And I noticed something. I go running every morning, and when I was out running the other day after this rain, I noticed there's just all this God knows what, some sort of oil car byproducts all over the roads where I was running at. right? Car tires are made out of petroleum, right? So your electric vehicles aren't going to solve this problem. Now, Europe's done a great job with its rail system. They have an incredible rail system, and they're able to, the cities are organized in such a way that you have these rings of green space around the towns. You have rails that connect the different towns, and most people don't have cars, right? You can bicycle around in these cities. There's a lot to be taken into consideration that is a solution, but it's outside of the solution set that we're really considering right now. Do we really need to imagine a world 100 years from now where everybody still has to drive on freeways to get to see their relatives in California? It seems kind of absurd that we don't have a nice rail system instead of the 5, or at least alongside the 5. So, I don't know. There's a lot more to this discussion of the environment than this one monolithic molecule, despite how important it might be for the actual climate in the future. There's more than climate in terms of taking care of the world that we live in. By the way, all this stuff is everybody out here lives on wells, right? And where do you think all that stuff's going, right? So, okay, I think I've had enough of climate for today. Let's talk about calendars. Slightly more saccharine discussion. So the rotation of the Earth is, by definition, 1 day. That's nice and convenient. And we talked about this a bit before. People have been trying to figure out how to fit the moon into that for quite a while. And people came up with the month. But, the moon really, its period is something like 29.5306 days. It doesn't neatly fit into 365. And that's been a huge problem for people trying to construct calendars, right? It's like, how do you, in some sense, the moon is a wonderful way to keep track of time, right? Because it's very predictable in that about every 30 days it's going to reset, and you can kind of plan your life around that. You can also plan your crops around the sun, but how do you mash those things together? And there's been a number of different kind of intriguing attempts at doing so. And the one that we're stuck with today has a really funny history that I'll tell you a little story about. But first, anybody been to Stonehenge? Yeah, all right. You should go. It's cool. It's going to get less cool, so go now, because they're building a freeway underneath it, from what I understand. A freeway, like a tunnel. I don't know, it's just... Yeah. But it's a really magical place, and they still have a big summer solstice celebration there every year, and all these druids come out, and it's quite a wild scene. But it's quite magical, and I think that the proper way to think about Stonehenge is something more like this. This is probably what it looked like in its own time. It's actually, and here we have a situation where you actually have a platform. There's probably a woman or a man on top who's, talking to people and divining the different ceremonies as they're taking place. But, and of course, all of the pillars are set up in such a way so that at different equinoxes, they're able to capture the sunrise at the particular place and orient people to the time of year. They also had some sort of a marker for the month as well. They would have some sort of stick that they would place each day around it. So it looks like they had their month divided into 3 weeks, not of 7 days, obviously, but in such a way that they could mark the progress of the month such that the actual moon and sun calendars would align, which is quite intriguing. It's actually really sad. We don't have a lot of information about the Celtic and Druid. So the Druids were the sort of priest class of the Celtics. Or the Celts. We don't have a lot of information about the Celts. Does anybody know why that is? Well, that was much later, actually. Yeah, before that, but similar. So the Celts, the priest class, the Druids, they passed all their knowledge along in song and in oral tradition, right? And that's really sad because what happened was when the Romans came up there, they killed all of them. They killed all of the priests very quickly. And that ended essentially thousands of years, potentially, of history of these people. And we lost it all. And the Romans turned out to be really good at extinguishing people from the planet and whole histories, which is really tragic. One of my favorite examples is the Carthaginians and the Phoenicians, who were arguably as big of an empire and as powerful of an empire as Rome in their day, but Rome actually wiped them off the face of the earth and burned their town to the ground. And it's quite tragic, and there's a whole history regarding that. So we've lost a lot of history as a result of that. So we don't really understand too much about these people, tragically. Of course, we see calendars all over the world, or calendar systems. The Mayans are kind of interesting. This is at Chichen Itza. Has anyone ever been there? Pretty cool place. I got the chance to go there when I was a little kid. Pretty awesome. They've got like the big pyramid there too that you've probably seen in some pictures and so forth. But this is their observatory. And the Mayans actually seem to have been much more concerned with, not with the sun and moon so much as with some of the other planets. They built a really, really fascinating calendar that is very, very different from everybody else's calendars. See if this will play. I don't know how to, I gotta turn off this sound. All right, so this is the Mayan calendar. What's really interesting is the Mayan calendar has 3 interlocking cycles. They have the 365-day year, which they have 20 different names for these days, 13 numbers, and it repeats every 52 years. They even have this embedded in an even bigger wheel, which goes for something like 5,128 years. And the last long count cycle ended in 2012. And I don't know if you guys are too young for this, but everybody was panicked that the end of the world was coming, right? But it didn't, or did it? I don't know. And so the interesting thing is people have dated that back to when this calendar started, and people have been pondering exactly what this was all set up around. And the Mayans were particularly obsessed with Venus, and there's some interesting cycles that concern Venus that might have to do with it, but no one can figure out exactly why they started their calendar in August of 114 BC, right? So about 5,000 years ago is when this calendar started, and nobody really totally understands that, and people have come up with all sorts of interesting ideas, like there was a supernova then that was perhaps signified the beginning of everything for them. Nobody really knows. It's a very perplexing calendar. I mean, actually, people didn't, in my lifetime, people deciphered the Mayan language, right? Nobody understood that for most of the archaeological history in the 20th century. And it was actually, the breaking of that code was done by one guy, pretty much, this guy, Michael Coe. And so we're very, very early on into understanding this. And of course, all of the later Aztec people's records were destroyed by the Spanish conquerors, and this is kind of a typical thing that we have to, that stuff still goes on today. And these wars that happen in the Middle East and the Far East, there's incredible pieces of history that are just getting wiped off the face of the earth. The cradle of civilization was essentially in Baghdad, right? That's where Mesopotamia and the Sumerians, that we draw all of our own legal and astronomical and scientific history back to. A lot of these have been destroyed even in modern times. So this is really tragic, and it's something we have to consider when we go mucking around in these places. All right, so let's talk about our calendar. Well, let's see how we got there. So the Romans came along, and the very famous Roman Emperor Julius Caesar decided he was going to standardize this. Now, he essentially recognized that the year was a little bit longer than 365 days, right? It's technically 365.2422 days long. And so it's about 365 and a quarter. So he came up with this idea of a leap year, which is that we account for this extra quarter day by just adding another day every 4 years. And you know what? That worked out pretty well. It worked out pretty well for a long time, actually. And so this calendar was very popular. But it is not the calendar that we use today. The problem is that makes it off by about 11 minutes every year. And by, 1582, that 11 minutes had added up to the point where the spring equinox was actually occurring on March 11th instead of March 21st, when it actually should be. So the Pope, Gregory the 13th, who was around in Galileo's day, decided that he was going to fix this, and came up with a very intricate system, which we still use today. which still includes the leap years. But there's this extra rule that only centuries divisible by 400 are leap years. So 1700, 1800, 1900, they're all divisible by 4, but not by 400. So they don't get counted as leap years. And this seems to work out pretty well. Interestingly, Pope Gregory, what did he do to fix this problem? He just deleted 10 days from the year in which he implemented this calendar. So all of a sudden, it would be like, I don't know, is it the 12th today or something like that? It would be like if it was just, okay, it's October 2nd now, all of a sudden, and we just do it all over again. So that's how he solved the problem, which I think is kind of hilarious in some way. All right, anybody have questions about calendars before we move on to talking about the moon? Yeah?
What about daylight saving? How does that work?
Ooh, daylight saving is an interesting thing. Actually, I saw that Oregon was going to ditch it. Did anybody else see that? Yeah.
I saw like everywhere was gonna ditch it, but nothing's like signed in place, and I'm gonna get depressed.
Yeah, in the back?
I just have a side question. I didn't get the sign-in sheet.
Oh, all right. Yeah, we'll make sure you get it. You can also sign it after class. Daylight savings, that's an interesting idea. I think, correct me if I'm wrong, the reason they introduced this was so that the children wouldn't have to be waiting in the dark at the bus stops in the morning, something like that, in the winter. Farmers? I don't know. I actually am not very well schooled on this. I do know that I kind of hate it also. And I've had some friends who tried to completely ignore it and just keep their clocks set, but this leads to you being late for every meeting, and it's not good. But no, that has nothing to do with anything regarding the calendar itself. It's just an invention that we've enacted, and I think the public support for this idea is dwindling in recent years, so I wouldn't be surprised if we lose it. My parents live in Arizona now. They moved there recently. They don't have daylight savings time, which makes it very difficult to figure out when exactly, if I have an appointment. We talk to them over Zoom once a week, my wife and I, and it's always very challenging to deal with the daylight savings thing because we're on the same time zone most of the year, except for then. It's very confusing. So we'll see what happens. I don't know. I think there is a measure, though, if I'm not mistaken, to get rid of it, although it hasn't happened in Oregon yet. All right. Let's talk about the moon. So, people, obviously, most of the ancient people were not too concerned with the physical nature of the stars and the planets and the moons, right? They were symbolic entities that reflected processes on Earth. They were using them to tell stories, sort of like how we use movies and music to do that today, or TikTok or whatever you guys watch. So back then, it was kind of a revolutionary idea. This gentleman, Anaxagoras, actually, who was a Greek scholar, actually was one of the first people on record to propose that both the moon and the sun were just giant burning rocks, essentially. It's big spherical rocks. And this is quite heretical, as you can imagine, to the clergy at the time. Greece was a really interesting place. It was not so much a country like the United States, as it was just a bunch of islands, and each island kind of had its own thing going on. It was really just a sort of diffuse culture with a lot of loosely related places. And I think that's why so much progress was able to take place, because there was no central authority necessarily that was regulating these things. And so you had really autonomous, and each island kind of had its own university, let's say, and its own school of thought, and you just had this wild proliferation of innovation and progress in a very short amount of time. Anaxagoras also came up with the idea of panspermia. He thought life existed all throughout the universe, and the way that life came to Earth was on some sort of comet or something like that, which is a really interesting idea that's often entertained in modern science. We'll do a little lecture on origins of life. I was actually thinking I'd bring my wife in to give that lecture, because she's more a biologist than me, and she's got really interesting ideas on that. But, life is perplexing, right? Because what's the first rule of life? I mean, something that the textbooks love to talk about is how people discovered that there was no life that could just spontaneously happen, right? And that's like a very first principle of biology, right? It's like, you're not going to just have a baby all of a sudden for no apparent reason, right? There's going to be somebody has to give birth to that baby. It's not just going to like show up. You're not just going to like have one just grow in your couch all of a sudden, right? So life seems to always come from other life. And so the proposal is, where did the life on this planet come from? Well, the natural explanation is it came from somewhere else, right? But that's sort of unsatisfying, because then it's like, well, where did that life come from? And where did that life come from? And at some point, you have to start investigating how inanimate matter, in some sense, started to possess this ability to orient itself autonomously. And it's a really interesting field of scientific inquiry, because in some sense, it's paradoxically based on the idea that life can spontaneously arise out of inanimate matter, which violates like the first principle of biology. But at the same time, it's something that we need to address, because, it must have happened somewhere at some point, right? I mean, or not. I don't know. It's very, otherwise you're looking at this eternal cycle. So anyways, he was a big fan of this panspermic idea that life comes from somewhere else. What else can we say? Actually, this Indian astronomer, in about, maybe 1,000 years later, was the first person to propose, Aryabhata, I believe is his name, wrote that the moon is actually not generating its own light. It's actually reflected sunlight, which is what we understand today. By the way, the dark side of the moon. You hear this all the time. There's no dark side of the moon, just so you know. Okay, the moon is being shone upon by the sun in all of its different orientations. It just looks dark because we can't see it, because we're facing it. All right, so anyways, people made various observations of the phases of the moon, made the Islamic scholars in the 800 ADs made some really cool estimates of the moon's diameter, which I won't bore you with right now. And then once people actually, when Galileo started championing the telescope, people began to be able to make out surface features on it and be able to actually really start to think of this thing as some sort of rock with terrain. These are actually Galileo's drawings, which are not bad if you think about it, for 1600, some of the first drawings. And then, of course, the popularity of the telescope took off. This is some of Robert Hooke's drawings. So Robert Hooke, we talked about him. He was the guy who had his inverse square law jacked by Newton. He was also a very, very astute microscopist, one of the first microscopists. So he was the first person to recognize that there was actually cells that constituted living organisms, which is pretty amazing. He looked under his microscope and saw some plant cells actually in cork, I believe. But he made these beautiful drawings. Actually, if you ever get a chance, just Google Robert Hooke's Micrographia. Just made these incredible pictures of tiny things that people had never seen before, the eyeballs on bugs and things like this, that if you imagine, for most of human history, people had no idea, right? You can't see these things. And you start seeing all the little hairs on the bugs and the cells in the plants. I mean, it must have just been incredible. So anyways, Robert Hooke made some studies of the moon where he actually was able to kind of elaborate on these terrain. And they actually match up pretty well to our modern pictures of the moon, which is quite incredible. One thing that's kind of fascinating, and we'll see this over and over again when we study each of the planets, is people were always convinced that there's something living on these things, right? And so this is, and actually I would say a large part of planetary research today is driven by the hope that we'll find something living somewhere. And I think it's at once an illustration of optimism and an illustration of cognitive biases that we experience, right? We just want to see ourselves everywhere. It's a very natural thing to do. And so, people held on to the idea that there was life on the moon actually until the early 1800s, I'd say mid-1800s. And it really came down to the establishment that the moon really had no bodies of water on it, and there was no appreciable atmosphere either. And so how could something live without water in an atmosphere? But it took them until the mid-1800s to really come to this. Before that, people were pretty much on board, even in the day that these drawings were made, that, yeah, there's definitely stuff living there. In fact, there's probably people living there, some sort of creatures like us. And that died a very slow death. Actually, when we talk about Mars, we'll see that people, even much, much later, believed that there must be life and human beings on Mars, because you can actually see seasonal changes in Mars. It gets these dark spots on it during its winter, or no, maybe it's during its summer. Don't quote me on that. We'll figure it out. It has these seasonal variations, and people thought, oh, that's plant life that's coming up, right? Because of the different ways that the light was lensed in our own atmosphere, it looked a little bit greenish to us. And we thought, there's definitely plants on Mars. And that held on into the 1900s, actually. So the Soviets were actually the first people to make it to the moon. This is a nice grainy picture they took. This is their capsule that they sent. This is the Luna 9, so that was their 9th attempt at it. And they actually managed to land this thing non-catastrophically on the moon and take this picture. And of course, people kept going back and kept going back. And actually, we're headed back there now. I don't know if you guys have been following this Artemis mission business. Pretty cool stuff. I've been thinking we should, it'd be really cool to have maybe an upper level seminar at this university where we look at the history of space exploration, because it's so rich and we just don't have time to get into it. But the struggle and the continued struggle to explore the planets and the solar system and beyond is just a fascinating, rich history, and a really, really cool endeavor if you think about it, in terms of making a backup hard drive for this planet, as wonderful as it is. It would be nice to have a couple of them, probably. So, yeah. So here we have it. There's the moon. Now, what makes a moon as opposed to a planet? Does anybody know?
It's not orbiting around the sun.
That's probably the main defining feature at this point. Exactly. So he says the moon is not orbiting around the sun. There's a couple of other definitions people have tried on along the way. One, that it has sufficient self-gravity to overcome these forces so that it can establish this spherical shape, which we call hydrostatic equilibrium. This definition is not incredible, because it turns out there's actually some really nice spherical bodies in the asteroid belt. Anybody watch The Expanse? Pretty good. You guys should watch it. It's so good. Expanse. It's a sci-fi. I think it was HBO or something. Yeah. Anyways, there's I believe it was Ceres, right? It was one of the stations in the asteroid belt. There's some spherical bodies that are not big enough to be explained gravitationally, and so it's not clear why they're spherical, actually. Although I would suggest that the answer is probably they're much older than people think, and they used to be a lot bigger. But anyways, that definition didn't totally work out. So the idea that it has to be in orbit around a star is quite interesting in terms of for a planet. So obviously moons are things that are orbiting planets instead of stars. There's this other problem with the definition of planet too. There's these very strange planets that we've been discovering, and we'll talk a lot more about them next semester, called brown dwarfs, which are thought to have formed just like stars, except they're not quite big enough to catch fire like a star, right? They don't have the sufficient mass to go into this nuclear chain reaction that sustains fusion, right? There's also been, in the last few weeks, some incredible reports from the new James Webb telescope where they're seeing these Jupiter-sized planets that are just orbiting each other in the Orion Nebula. Right? This is very perplexing to these scientists because, well, they're not able to have formed without a star system according to the conventional formation ideas. And we deal with a lot of the solar system formation next semester, but they're really challenging our ideas about how where these planets come from, the stability of solar systems. I'm actually having a really good. I'm looking forward to this. I just met with this astronomer yesterday. He's in France. I can't remember what university he's at, but he's going to come on the podcast, and he's looking at the potential for actually how he does these alternative calculations. Like, if we changed the mass of the planet this much, how would that change the solar system? If we changed the orbit this much, how would it change? He creates all these different worlds, right? These kind of counterfactual, alternative universes, and imagines all of the considerations. And one of the things that he's coming up against is that actually these solar systems have great potential for change and for ejecting planets, right? And so there's also the realization that there are a lot of these rogue planets, right? Some estimates are as high as billions of them in the galaxy, right? More than one, maybe several per each star. So the idea that a planet has to be orbiting a star might not be appropriate either, right? And then that opens the can of worms. Well, where do these moons come from? Because could some of these moons have once been planets themselves? That's an interesting question. So anyways, these are all wonderful open questions. This is that process of hydrostatic equilibrium I was talking about. You basically have the internal pressure of the planet as it's pushing outward. It's heated by compression, and then you have gravity holding it in, and you get a sphere as a result of it. Sort of like a water droplet, but different forces. And here's a couple. There's Ceres, right? These are a few semi-spherical moons that are not big enough to sustain hydrostatic equilibrium, and yet they're spherical somehow as a result of it. Why? We don't really know. So maybe they're really, really old. I guess it's as good a time as ever to talk about how old all of these things are. The interesting fact is that the oldest things that we've ever found in our solar system are 4.5 billion years old. And so, the conventional interpretation of that is that the solar system itself is 4.5 billion years old, which seems totally reasonable on its face. However, there's some problems with that. So our modern dating methods are wonderful. We use this radiometric dating method, which essentially allows us to look at how these heavy isotopes, these heavy atoms, decay very predictably over some very long time scales into lighter isotopes. And what's cool about this dating method is you can look at different elements in one sample, and they each have different curves of decay. And so you can kind of cross-check them against one another, right? And so even if there's some contamination or something, you still have another isotope which you can check. And if you get the same date from each one of them, you can be pretty sure that your date is accurate. But what is that date actually measuring? Well, all that date is measuring is the last time that rock was melted, okay? So what we really know is the last time any of these rocks were melted, not the last time, but the most distant time these rocks were melted was 4.5 billion years ago. That really opens the door for the idea that maybe the solar system itself is much, much older than that, but perhaps all we're able to see is the last time these things got cooked. Could they have been cooked by lots of processes, collisions, supernova nearby? I mean, one thing that's really interesting is, I don't know if you guys are aware of this, but almost every single star that we've ever seen has another star that it's orbiting. Our star does not, which is very, very strange, actually. So you might ask yourself, where's our partner star? What happened to it? Was it cataclysmic in some sense when it went away? Did this change things? Did it snarf up a bunch of the other planets that were around at the time? Nobody knows. But it does seem to be a very, very unique system among others. In fact, most stars have 3, 4 stars in their orbital systems. So we're a very, very strange star system in that sense. All right, so let's talk about how the moon was formed. I have a video here. Will it play? Yes. Okay, so this is how people thought the moon was formed only 10 years ago. And I'll play you another video next about how they thought the moon was formed. So they originally thought that the moon was formed, this was only 10 years ago, that the moon and the Earth were formed at the same time. And this is totally reasonable because, they have very similar elemental compositions, the Earth and the moon. Once we went there with the Apollo missions, we brought back rocks, and we saw, hey, these are basically the same as Earth rocks in terms of their isotopic abundances and so forth. So they must have formed at the same time. But that's not what people think today, actually. Let's just finish watching this. So there were some big collisions that happened, led to a bunch of debris orbiting, which then leads to cooling. You see these dark spots on the moon, they're called mares, which is Latin for seas. People, of course, originally thought they were seas, and hence why they thought there was life. And as the mares cooled, then all of these asteroids that were ejected started raining back down. And I guess I could have put this on 2x. There we go. Huge bombardment cycles. And at some point, you get the moon as it appears today. But this is not the theory that we think is actually true. All right. All right, so there's this other theory, which is the Theia proposal. I'm going to have to start this one manually, I think. So the new idea is that there was actually another planet in orbit called Theia, which impacted the Earth. And we'll see a little movie of that here. And people have come to this conclusion because, of course, they find pieces of the moon or pieces of rock that they believe are from the moon all over the Earth. And so this is the most popular idea today. Again, you can see that this thing that's glowing is supposed to be the Earth from the early days. So this is, again, supposed to have happened somewhat early on in the progression of our solar system after its formation. And the idea is that these planets smashed into each other, essentially liquefied both of them, and then they cooled into the form that we see today. So that's an interesting proposal on its face as well. It'll be really interesting. So there's something that's happened recently. I don't know if any of you guys have been following this, but there's this Harvard astronomer who has become obsessed with these interstellar objects that have been passing through our solar system. Does anybody remember these headlines about this very strange one named Oumuamua that came through the solar system? Did anybody see this? Yeah, so there's this very, very weird rock that came from outside the solar system, which is something we didn't think was possible prior to this, essentially. And it came very close to the sun. It made something like a right-angle turn at the sun and then left. So there's this Harvard astronomer who's like, that's definitely an alien spacecraft, right? This guy is like not a lunatic completely either. I mean, he's a lunatic in the best sense, but he was actually the longest running chair of the Harvard Astrophysics department. So he's not just like some, crazy dude. And Avi actually went, I've actually had him on the podcast a couple of times. He's a really interesting guy. And he actually just, he realized that he went back and looked at all of the Defense Department's data, and he found that there was actually a couple of other rocks that seemed to have come from outside the solar system over the last 20, 30 years. And he noted one that came through, I think, maybe 5 years ago or something, and he saw that it crashed into the Pacific somewhere. And he just recently mounted an expedition out there to dredge up the ocean and try to bring back some of this sample. And why do I bring this up? I bring this up because what will be really interesting is if, when they do the dating measurements on these interstellar objects, if they come up with the same 4.5 billion year mark, right? Because if they do, for me personally, that says that this 4.5 billion year cutoff means very little other than that's about how long we can expect something to fly around in the universe before it gets cooked by something else, right? So, in other words, there's some statistical distribution for how long something's going to survive in the universe, in space, before it gets melted by some process or another. And so then we've really opened the doors up to how old this place is, Because what if our planet isn't just 4.5 billion years old? What if our planet's trillions of years old? Well, you might say it can't be trillions of years old because the universe itself is supposed to be only 14 billion years old, right? But there's some interesting challenges to that proposal as well, which I don't have time to expound upon in this course, but we'll deal with it next semester. So this dating stuff is quite fascinating. Again, it's an interesting piece. It's an interesting point where the measurement techniques are extraordinarily accurate, but the assumptions which go into interpreting those measurements are certainly open for revision in some sense, potentially. Could they be correct? Absolutely. But I think this interstellar dating will solve that problem. So every time I talk to Avi, I tell him, man, you've got to date those rocks. We got to figure this out. And we'll see if he does. I'll call him up again soon. All right. Okay. Let's see, we've got about 10 minutes. Let's try to make our way towards the eclipse because we want to get ready for that. So, how come? So have you guys seen a lunar eclipse before? Yeah? Lunar eclipses are pretty cool. You got to be willing to stay up at night to see those things. But, you might ask yourself, why is it that we don't have eclipses all of the time, right? The moon is always going around us and in front of the sun. And this is obviously, we wouldn't even have phases of the moon if this wasn't the case. But the fact of the matter is that the orbit of the moon is not perfect, right? It's not this perfect circular path. It's actually an ellipse, just like all of the other orbits, and that ellipse is precessing in its own right. That's why it's not in the same place every single cycle, right? And so this drift also happens in the vertical direction too. So as you can see here, it's wobbling a little bit in its plane. And so only every once in a while is it in the exact right position. It's called a node, right? A lunar node, where it's actually able to get in the way of us and the sunlight, and vice versa. The Earth is able to get between it and the moon so that you get the lunar eclipse. And so let's look a bit about how these phases are organized. So as you can see, I believe maybe this is from your textbook. What's actually happening is shown on the interior circle there, right? So the moon is being illuminated at all times on one half, and it's dark on one half all the time. But that's not what it looks like from Earth, right? Because we're on this interior track, and we're looking out towards it. So we see these different phases as we go around it. Now, as you can see, when it's completely opposite us, we get the full moon. And that's interesting because the only reason that we even see full moons and the Earth doesn't cast a shadow onto it is because of that precession of that orbital path, right? And every once in a while, the Earth does get in the way, and that's when we get the lunar eclipse. So let's skip this. Here's another little way of looking at it. This kind of shows you where the moon is with respect to the rays of the sun at each path, so you get some clue about where it is. It's actually quite interesting because if you familiarize yourself with this diagram, you can start to get into the sense, you can actually get a real sense of place when you look up at the sky at night, especially if you get so lucky as to see one of those moons that's in the day a little bit, or at sunset or sunrise. Sometimes, actually this morning, it was a very beautiful moonrise, or moonset, I guess, with the sun. And you can really get this sense of exactly where the sun is and how it's casting the light upon the moon. And you can also get a sense of where the moon is in its path around you, which is really fun to have that sense of place with respect to the sky. Of course, the moon is turning, the Earth is turning. The moon is not turning. The moon is actually tidally locked to the Earth. This is another feature, I think, which would make a good definition of what a moon is that they seem to always have one side facing the planet. In other words, they're locked up. This isn't the case for some of the smaller little bodies, the less rounded ones as we get out into the deep solar system. But almost all of the large moons in our solar system are tidally locked like this, so only one side is facing the planet, which is interesting because it implies some sort of deep stability, some very long-lasting stability. And I think this is one of the bigger problems with these impact hypotheses for the moon, is that the idea of stabilizing something to the point where it doesn't even rotate anymore is a bit of it's difficult to swallow, I think. So yeah, so because of the fact that our planet is turning, we're moving around the sun. The position of the moon at moonrise, let's say, or at sunset, which is when you'll probably be able to start seeing it for the most part, is changing a little bit. I think it's rising a bit about 50 minutes later each night as it moves eastward. And of course, as the inclination of the Earth is more or less exposed during the seasonal changes, the path of the moon seems to shift apparently from our position as well. So in September, you have this much more oblique rise, and in the summer, this is in the spring, I'm sorry, it's much more vertical. So you have this, you can have more atmospheric effects. That's why you get these very red moons in the fall, because it's coming through all of this atmosphere, right? It's rising much more slowly. It's spending more time along the horizon, essentially, which is pretty cool. I guess they call it the harvest moon. All right. Let's talk about tides a little bit. tides are actually quite confusing. So the basic principle that the moon is exerting some force upon the oceans and dragging them about is easy enough to understand. I think I understood this as a child for the most part. But the way that that plays out is actually quite complex. And in fact, the distortion actually tends to be on both sides of the planet, right? And this is a bit difficult to comprehend with just simply the pull, because you would expect that it's going to just yank all of the ocean to one side. But this isn't what happens. And the predominant view is that this is because as it pulls that ocean towards it, it gets it cycling in this sort of, it has this inertia to it. We talked about inertia a bit, the tendency of things to want to stay in motion. And so it's actually sloshing over on the other side of the planet at the same time it's being yanked over here. Actually, the intricacies of the tides are also not as clean-cut as that diagram might have you believe. So, the tides we see are affected by everything from weather, storms, right? Storm surges, to the shapes of the continents. There's places that experience very little tides. There's places that experience extreme tides. And it's very heterogeneous. It's not so nice as this diagrams usually show, which makes it very difficult to predict, actually. And people have been obsessed with this for hundreds of years because it's important for navigation. There's another feature, too, about tides. It's actually a bit of a lag, which is quite perplexing. So the Earth, as you can see, it's turning really fast compared to the moon's progress around the Earth. And all of that friction of the Earth pulls that blob of water ahead of the moon, actually, a little bit, which also changes things. Adds some nuance and complexity to the system. We also have this idea of king tides and neap tides. Have you ever heard of these? So it's really fascinating. I spend a lot of time down in San Francisco, and one of my friends lives out in Bolinas. And sometimes when we go out there, like half of Marin is underwater, actually the freeway system and everything, because they have these king tides that come in. And the king tides result from this collaboration of the moon's pull with the sun's pull. And so you can see that depending on how these pulls, the moon and the sun line up, when the moon's very far away, you actually can get this king tide. You actually get it, spring tide. You get a very, very weak tide here, the neap tide. And then when they synergize, you get an even greater pull. So you really have all of these different complexities of these different orbital resonances that are pulling and leading to the tides that we recognize. There's also a lot of water underground, too, that's at play, which is quite fascinating. And I think we'll put a pin in it at this point. And what I want to say is that in terms of things that are on the move, this has been a really fascinating one. When I was a kid and taking astronomy, the predominant idea was that all of our water on this planet came from comets, right? But I remember being like 10 years old and being like, that's a lot of comets. You ever been to the ocean before? It's like, I don't know about that. So now they've discovered that actually something, upper end estimates are as much as 6 times the amount of water in the oceans. Lower end estimates as much as 1, right? As equivalent as the oceans are underground in the form, not in terms of liquid water necessarily, but they're found at the transition zones, the different layers of the earth underneath, in the form of this hydrated mineral. It's actually, I believe, some sort of magnesium which can bind waters to it. So there's a tremendous amount of water underground too. And I think that's really, really something to think about. And that'll come back and play into our formation process when we talk about that with the Earth. But let's put a pin in it. I want to wish you guys a good weekend. And come see me if you have any questions. And I'll see you on Tuesday.